Okay, I'm going to explain to you every one of these little pictures, and I'm going to tell you right now, these are the smallest particles that exist, the same as these here. That just happens to be in green, but you see, that's a photon. It consists of 2 muon neutrinos and 2 electron neutrinos, and so does the red, and so does the blue. And these are the smallest particles Fermilab has ever seen, and I agree, because here they are right here. So let me get into my research. You tell me what you think. Okay, my friends, hold on to your hats. I'm going to go back to the beginning of my physics work. I'm talking way, way back, 1968. Now, I just saw this. New quantum effect could mean the Kondo state isn't what we thought. And this is ultra cold physics. They don't understand cold. That's the key. They don't understand so much about electronics and about what makes up the nucleus. It's just incredible. So let's get started. And I'm going to tell you, this is going to be a trip for anybody that thinks they understand physics. I'd like to hear what your thoughts are on my explanation of things. Okay, my friends, this is going to be fun. This is revisiting days of yesterday. Now, I did all this stuff, I mean deep, when physics and quantum and all that stuff was really getting started. And I had to understand everything about it, all of the difference, what everybody was claiming, let's put it that way. And I wanted to see if I thought they were right, and I said, no, they're not right. I said, it can't be what it was, one big giant positive and a couple of little negatives floating around. It's impossible. They just go like that. So I said they all have to be dipoles. And everything's about the dipoles, dipole molecular moments and all this stuff. And then I ended up with this. The transfer of energy is from light to atomic vapor. Light is atomic vapor. It's the smallest bits and pieces of particles there are. And then I went on to all the chemistry and, all bonding and chemical reactions, electrostatic forces, and so I've been through the whole roll with this. I've done it all, and I just kept going because I realized they were wrong. It had to be dipoles. So now I'm going to go right back to the beginning when I started, and I'm going to explain to you what I found then and what it still is exactly the same thing today. Only now I can see it because we did the light experiments, and there's no question. Now this is Yale. And I took the quantum courses at Yale, and I took them at University of Geneva too, just recently. This goes back about 10 years, 12 years, something like that. Hold on one second. Now, I have kept up on this stuff too. I have books about everything and tons of different ideas about things. It's just what I do. And a friend of mine wrote some books. I have nothing to do with the books. They're not mine. I don't profit from them. I don't participate in them. He just took my papers and put them into books, and nice little coffee table books. They're not expensive. And this is about my electron flood theory. And he also puts in here my other stuff, that was the Mudfossil stuff. So it encompasses a little of each, but things have to change. We have to start to look at what is right in our faces. And this is Professor Shankar at Yale. Here's how they're treating this quantum physics at Yale. And this is 10 years ago, and I don't think they've changed much. Okay, as you know, I have the electron flood theory, which says that everything is a dipole, and I do understand the electrons, and I understand the quantum, which I will present to you, and I will debate anybody that's in the quantum realm that has some kind of serious discussion to have. Okay, my friends, I go a very long way back with the dipole electron flood theory. This was back from 2019, but I go way back to 1968 when quantum was really in its heyday. It was just getting started. What are these particles made out of? How do they react? What's all this? What's that? And they were really deeply investigating these things, but the tools weren't there yet, and it just wasn't ready. And I could see that they were on the wrong track. They were looking for one huge proton in the center, a positive, and then little negatives floating around. It just wouldn't work that way. It had to be dipoles. So let's just start with that. And everything is a dipole. And it is. As it was then, it is today. There's no difference. Now, this is what they say at Yale. Now, this is Professor Shankar. Now, I took the quantum, I looked at it. I have more information about this than they do, trust me. And he admits it. Listen to this. Listen.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively. And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So, in some sense, the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
well, what can I say? Okay, my friends, let's just start with this. What is the goal of physics? The ultimate goal of physics is to identify the smallest building blocks that exist. These are the building blocks which the universe is built, and describe the laws that govern them. Until we do this, our understanding of nature, all complete of nature, is incomplete. We don't understand it whatsoever until we understand what it's made out of. And I'm going to tell you right now what I think it's made out of, and then you make your own decision. Okay, my friends, this is really over the edge. These are the particles that they have found at CERN and then Fermilab. All right, these are and these are colliders and smashers, and they see these tiny little bits, and these are the smallest ones, but they see all kinds of other stuff too. We use light instead of protons, and we can actually see these particles attached together in their light form. And then we were able to divide them, smash them apart in the Venturi right here. So as the light came through, it was attached just like these. That's what's called a photon. Half of this is what I call a dipole electron, which means it has a black and a white, which is a dipole. And when they hit the Venturi right here, the black actually separates from the white, and then it returns back together here, creating precisely what they say they see at CERN and Fermilab is muon neutrinos, electron neutrinos. That's the black and the white. When they hit this kind of a medium, in theirs they hit heavy water usually, the black goes on its own. It's called a sterile muon, which is these black ones all by themselves. And then the white goes into an electron shower mode, which is it's exactly what you see. So, where did I show you this? Sometimes things fall into place that just blow my mind. Where do you see this? This is absolutely bizarre. I can't believe this. This is the ultimate goal of physics, to identify the smallest building blocks. I agree. Which the universe is built of, and describe the laws that govern them. Until we do this, our understanding of the nature will be incomplete, and reaching this goal will challenge us for the foreseeable future. No, it's been done for quite a long time now. But researchers are using an enormous facility in red in Europe to study these. This is the Large Hadron Collider. You don't need that at all. They're just breaking big blobs of matter and turning them into just debris. All right, and they're talking about heat that reaches that of the sun. Classical questions, modern progress. What are the smallest, most basic ingredients of the universe? The query is as old as science itself. Greek philosophers asked this question 2,500 years ago. Modern scientists know a great deal more. No, they don't. They're not even paying attention to what's right in front of their face. But even today, researchers fall short of looking at what's a reality, yes, of a definitive answer. And so after 2 millennia of investigation, many discoveries, studies continue on this age-old questions because they won't look at the answers to it. The answers are right here, right in front of their face. And they're just trying to make these huge colliders to make tons of money. We use light, and we separate it and have the particles they're looking for. These are Higgs fields. Nobody can disagree with that. These are Higgs fields because of light being separated and the electron shower hitting the actual muons and turning back into matter again and into Higgs fields. And they have the same thing. They see them here. This is their Fermi lab, or CERN. I guess that's CERN, LHC. But when they hit, they just have debris everywhere. When we hit, we can see the actual particles. All right, this is our stuff. These are the actual white particles recombining with the black particles, creating Higgs. All right, they have just this debris. They just have debris. They hit huge things together, big balls like this, smashing them together, and everything goes flying. We're using this, so we can't get up to that mess. And we see what happens when they hit, and we can use the different colors, which are the different frequencies. So here's your green. That's a photon. That's the muon part, which is the black, and that never changes size. Never ever going to be. It's going to be always the same size, and it is only attractive. It doesn't glow, and the only reason we can see it is it's impeding the glow around it, because it doesn't radiate, it doesn't absorb, it doesn't emit, it doesn't do anything. It's a bowling ball. These, the white ones, want to get attracted to the black ones. They're the ones that really want to suck into the black ones, because when you put your stuff in your battery, think of this now. You have a battery, and it's empty. There's no charge in it. And you charge it up. What are you doing to that battery? All right, you charge your battery up. What did you do to the battery when you charged it up? Well, I plugged it in and electricity went into it. Well, how did the electricity go in? What does electricity look like? That's all you put in was this white. No black. Black stays out. And the white has no weight to it, basically. Almost zero weight. Virtually no weight at all. So that way there, your battery charges way back up again. You drive around the town a couple of times, and all you're using up is the white. And it never changes weight. And the white, so desperately sitting in that battery, wants to get back to that black that it will go through a motor and make your wheels go down the road. And so the white is really wants to get back to the black. And that's the whole key of a battery. That's the whole key of electricity. White wants to get to the black. Okay, so again, we're looking for the smallest component of matter. And this is Don Lincoln, and he's saying the ultimate building blocks. Nearly a century ago, scientists realized atoms are made of even smaller objects. The two tiny types of particles, protons and neutrons, were found in dense cores at the center of atoms. A third type of particle swarms around the core like a cloud of hyper-caffeinated mosquitoes. The third particle is called an electron. Well, this is not correct. They are all made of the same particles, and they're dipole electrons. There's not a swarm of negativeness around a big ball of positiveness. All right, here's Don Lincoln again. Protons, neutrons, and electrons were then thought to be the smallest building blocks of matter, but their classification would soon be usurped. About a half a century ago, that's when I was doing this stuff, 1968, scientists discovered that the proton and neutron are composed of even smaller particles called quarks. Well, no, they're called dipoles, dipole electrons. Thus far, the electron has resisted all attempts to find a smaller particle within it, because they don't understand what an electron is. It remains the best known member of a class of particles called leptons. Quarks and leptons have been observed and are considered settled science. No, it's not settled by any means. Okay, this is really kind of interesting, because he's saying his quarks, this is settled science. Well, it is not settled. And I had direct interaction with Don, and we did not get along well. And he told me I was a tinfoil hat guy and never contact him again and just stay away from him. And I said, I have the evidence to show that I found the particles you're looking for. He says, never contact me again. So that's what happened. He's saying, as of the writing, observing the tiniest particles in the universe, as of this writing, quarks and leptons are the smallest known building blocks in nature. and they are very small indeed. The most powerful instrumentation can see objects smaller than a proton, but quarks and leptons are too small to directly image with modern equipment. That's just nonsense. Yet, despite their tiny size, many researchers wonder if perhaps quarks and leptons are built of even smaller things. They're made out of the muons and electron neutrinos. And he's seen them. I can't understand why he doesn't understand what he saw. Okay, this is what Don Lincoln saw. He saw the black and the white particles, or red. They can be red, green, or blue, basically. And they split, and he claims exactly what we claim. This has no mass to speak of and a hell of a lot of burn, and this has all the mass and no burn. And he calls these point particles and fixed particles. He says, and then he's talking about the observer effect. Listen to this. He says, if you magnify an extended particle, and the extended is this one, it will look bigger. A point-like particle will not change in size. That's this one. But the more closely you look at it, the stronger the field surrounding it becomes. It's only because you're pushing into its field. It's not because the field gets stronger because you're just looking at it. And that's what they always thought, the observer effect. It's absolutely amazing that they could think that. Anyway, they did. Now, what we did, we used CMOS. What is CMOS? And when I say CMOS, it's CMOS. Somebody the other day says, how could you use CMOS? I think that just grows in the ocean. Anyway, CMOS is a receiver. It picks up radiation and turns it into colors. So what we did, it's right out of this cell phone. And this cell phone goes right back to this time. This is from 2012, this cell phone. He dated his 2013. Now, I was interacting with Don Lincoln shortly after this article, I think. It was right in that time frame. And I said, we found your particles. And of course, like I said, it didn't go well. But here's his summary. And this is Don Lincoln. It says, in summary, extended particles have a fixed size. That's the black one, and it never changes. He's right. I agree with that 100%. They may have a fuzzy edge around them. Yes, they do. The point-like particles are mathematical extractions with zero size. Now, I can't totally agree with that. I know there is some weight to them. There is some weight to them. Very, 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 very little. And I know about this too because I worked with weights and measures and understand that a cold set of weights weighs differently than a warm set of weights. And all that is extra electrons put into it to warm it up. All right? No difference whatsoever it's identical stuff, because when it's cold it weighs a certain amount and when it's hot it weighs a certain amount. Which one do you think weighs more? The hot one weighs more. It's got more electrons in it. And I know this because I questioned them thoroughly until I was satisfied with the answer. So there is no zero weight. So he's saying even zero size particles have an extended field. Yes, absolutely, they have an enormous field. Look up hydrogen. It's got a 21 centimeter line. 21 centimeters is the wavelength that it controls outside of its core. I believe that's what it means, 21 centimeters from the center of one hydrogen. They're huge fields. That's why when we crushed them down into the Venturi, they just exploded. And only the white could get through and the black bounced back out. And I show that over and over and over and over and over and over. And here it is right here. We accelerated the light. You're not supposed to be able to do that, first of all. That's not a problem to do whatsoever. And the particle itself is right here. It pulled right out of its wave. The wave is the field. There's no particles out there. It's just the field. And it's got to go through, but the particle is in the center, and there it is. And then it turns into a photon. It goes through neutrino phases into full photon, and then it explodes here. The black can't get through. Only the white showers, and then the black reattaches here. And let's look at that close up. All right, these are the particles, just exactly like Don Lincoln said. The black one has a fuzzy edge around it. Yes, it does. That's it right there. The white one can get big, it can get small, just like it is here, and the reason it's getting big here is because it's going that way, concussing. It will charge up and flip. That's what the muon wobble is. All right, now, this is a photon. Half of that, just the one black and one white, is an electron. An electron will try to incorporate into something as heat. It does not want to stay by itself. It's a reactive particle. A photon is two of them back to back. It's just sort of neutralish. It will bounce off of something back at you because it has that big balloon field, boing, and it bounces back. Now, what color will it bounce back? Depends on what it hits. All right, same light's hitting this. We see all different colors. So obviously it depends on what it's hitting. These bounce back blue, these bounce back yellow, and it's because of whatever the material of that paintish stuff is. That's the color you get back. It's just a bounce. It depends on what color you started with, what color you get back. Because you got green, here's the green, same particle, see it? Did I show you the particle? Hold on. These are the neutrino phases as they come into becoming a photon. And you always see them straight up and down. That is another point that I want to bring out. It's the polarity of the Earth creates the up and down spin. Now, that's the green, and here's the red, same stuff. Same thing, same particle. And as it comes through, you see them? These are the neutrino phases. They're building charge, and then they flip this way, and then all of a sudden they turn into these things, which are photons. And then at the Venturi, they explode and split into the white and black particles, and that I show as well. Oh, where is it? Well, there it is right here. Acceleration. The black can't get through the tiny little slit. The slit has to be tuned right, and you have to have the correct Venturi. And the Venturi just means it's like a funnel. This is what we use. This is it. I'm not kidding you. I'm serious. A little pulsed red laser like that. This is exactly the laser. And then a couple of finishing nails, really tight up close, and then picked up all this stuff on a selfie side of this exact same phone, Samsung Galaxy S3. And this came out in 2012, and Rod Warren over there in Australia was trying to do the double slit experiment. And he was posting pictures all over the place of things that he was doing, and nobody was paying any attention, you know, and I saw it and I said, whoa, this guy is onto something. And Rod graciously worked with me for several years, and we sort of went this way and that way, but he's got to be recognized as the guy that figured this out. I mean, he did it just by accident. And I said, Rod, can you do this? Can you try this? Can you do that? And he did all the things I asked him. I really did very little on this. I have everything that he had, but I didn't do the work he had. He did the work. He did the work. I needed to understand this, and I needed somebody that was capable of doing this fabulous work he did, and it was fabulous. This is fission. That's fission. The black came away from the white. No way in the world you can say it's not fission. Came back together, that's fusion. Simple as that. He created fission and fusion. I don't see, there's no way you can deny that. And because this is the particle, and the red and the black is the blue, they're all the same particles. They're stuck together. They're fizzed together. When you break them up, they fission. And then they fuse back together again on the other side of the Venturi. All right, all of this stuff is accounted for now, and the only smallest particles there are the little black and white ones. This one here and that one there, that's it. You know, that could be blue, that could be green. The green we have the same, like I showed you. The green is the same particle. All right, the green glowy stuff around it. The black, just like the red. And the blue is the same thing, only the blue is so fast you can't even tell. See this like here? It's coming through the Venturi. Starts to slow down. And by the time you get out here, you can see that it is a photon with two whites. Back here, it's spinning so fast you can't even tell. And the reason you see light as a wave, it's not really a wave. It spins in a circle. Let me show you. All right, think about this now. They see these interference patterns, they call them. You see these little bumps here? And what they think is two slits the double slit experiment. And there's no reason to use two slits. One slit is what we used, and we see the same patterns, exact same patterns. And so they say there's two slits, and the reason you see in these is because the waves flap like this and push each other back and forth, push back like this, and then spread out a wave like you see on the water. They can replicate that by punching the water, and you see the wave come out. It looks very similar to that, I agree. But what happens here is the light, because it spins, it sometimes spins off that way, sometimes it spins off this way. But these whites hate to be next to each other. That's why they glow like crazy. So here they just push each other out, and it sets up lines of interference, and they are very, very specific. They sort of congeal here and there, so you see them like a spray out, but they are very specific. They do not want to be next to each other. And this is the spin of the light. That's what light does, it spins. It doesn't flap like this. If you look at it from the sideways, yeah, that looks like a flap. That looks like it's like going up and down and up and down. Yeah, that's fine, but it's really coming forward like this. And the red is shifted way out here. Real slow. Green is somewhere down around here, and blue is like, it's just rocket ship. So that's the difference between light, is the speed of the spin. As I showed you, look at how fast the blue is spinning. And the white, and I mean the red, and the green spins pretty fast too. But not like the blue. The blue is the rocket ship. And then you get, at a certain point, it goes into what they call the ultraviolet catastrophe, where you have no electrons left. The electrons have just completely been stripped off of the big heavy black core, and there's no more electrons to give off. That's the ultraviolet catastrophe. All right, so here's my claim. Everything consists of the W and the Z boson. And what are those? That W I'm going to call the white boson, which is the white glowy part, and the Z is the black, which is the muon. So that would be a muon, and that would be an electron neutrino. The two of them together, slamming together, cause the Higgs fields. All right? You take two back to back, because these are what they call glue. They glue together, and they make a gluon, which is a black and a white one together. To me, that's a dipole electron. It's the black and white together. You take two black and whites together, and you have a photon. Precisely what I showed you. All of the rest is just mumbo jumbo, because all they are is made of these two particles. Now, they're in different phases of energetic value, yes. In other words, at this point, and this point here, these photons have a different energy value. That's their neutrino phase. Yes, I agree with that. But the particles that actually exist, the only ones that exist are the black and white ones. And really, it's a Dirac neutrino is the black and white. Here they're seeing the majority is when they're in a state of flux. But normally, well, let me put it this way. They're either made of the black and white particles stuck together, or they're apart. That's all. But that's all there is made. This is it. Sometimes they look like they're in the same state of energy, but they're really not. One of them is white and one of them is black, and the black one always attracts the white. And the black one never changes. I don't think you can break that apart. I don't think the black can be broken at all. I think that's it. Not only can you not break apart the black, you can't shower with the black. You can shower with the white, but not with the black. You see this? This is only from a couple of months ago. Cherenkov radiation happens when electrically charged particles, such as protons or electrons, traveling faster than light in a clear medium like water. When this happens, the water molecules and particles interact to give off light. They literally bounce the light off them. Okay, my friends, this is the Department of Energy. Department of Energy. Okay, and what are they talking about? They're talking about Cherenkov radiation. Now, this is only a couple months ago, and I've been posting this over and over and over. The Cherenkov radiation shows the particles of light when we use the Venturi and just use a pulse red laser. So they're seeming to to start to come around about this, because they're saying Cherenkov radiations happens when electrically charged particles such as protons or electrons traveling faster than light in a clear medium like water. Well, we did it in air. We didn't have to go to water because we crushed them in the Venturi. What they did is they smashed them into a new medium, and that's what caused the particles to just splash off. We forced them to come through at our focus. We focused them, and we caused them to give off light within the air itself. We didn't have to go to a new medium. All right, so here's what they're showing. Cherenkov radiation, we just talked about, divides the light. And what it does is it creates the muon, which is the black ball, and I'll show you, I think I've already shown you, or will. The black and white are attached together. The black one goes off by itself. It's called a sterile muon, where the electron portion, the electron neutrino, which is the white ball, turns into a shower because it hits other ones. They are all like big basketballs too, and the whole thing, get out of the way, get out of the way, get out of the way, and it creates a shower. And it's very, very high energy because there's a lot of interaction, and because of the pulsation of the laser, it keeps slapping it through, bang, bang, bang. And when it does, these have to go somewhere, and they keep slapping everybody in front of them. This is precisely, exactly identical to what you're seeing here. The black neutrino, the muon neutrino, is this ball. These little black balls. They never change size. They don't glow. They don't emit, absorb, reflect. They don't do anything. All they are is an attractor of the white, and that sucks that white back just as hard as it can possibly. This is the strong nuclear force, is the white being attracted to the black. You see how instantaneously they come back together. And this is where the Higgs fields are formed. All those spinning, as the white hits the black, and they just start spinning like crazy. So here's exactly what it is. There's the showers, and there's the black muon. All right, the only way you can look at it, this is fission because they were attached together before, and then when they come back together, it's fusion. All right, now, this, I have everything to prove what I'm saying. And what just happened here is this. These are the Higgs fields. That's where that white smashes into all of the... Black has to be everywhere. It's got to be ubiquitous. They're just waiting around for white ones to hit it. Because they all just... That's an electron shower if I've ever seen one. I mean, this is the only time I've ever seen one. So now, you see that little spritz right there? You see it hit this particle? That's turning... It didn't keep going. It didn't keep going. It hit it, and it turned it into a spinner. And all of the outside edges have the strong force. You see them, how they all have the strong one on the outside? That's where they're getting hit and spinning. You see them? And they're just spinning into like these Higgs fields. Now, I'd like to do a little more work on that, but they are Higgs fields. Of that, there is very little question. And they see them here. These exactly same things, only they're so huge that they just see them in big balls of debris. So that's from CERN or LHC. And here it is right here. It's just debris. And they see there's different colors because there's different energy levels of particles. Here's one, there was one here that was really good. Here it is right here. The red ones stick around because the highest energy ones, the blue, the green, right in that area, they take off and they don't come back. The green is, I mean, the red is sort of floppy, and it's always on the periphery anyway, so it's just getting bounced and staying around. In ours, they all, they just scatter. You see, all of the particles turn into white because we're crushing them in a field. We're doing better than they are at CERN. They're just trying to hit them head on. And normally they were not going to hit head on. They're going to glance each other. And then they're going to see a little debris coming here and a little debris going there. Not like this. We can focus this, and we should be able to harvest that. I don't see any reason we shouldn't be able to harvest that white energy right there. Push it down into our batteries and then use it later. because this is the key to to charge up your batteries. You have to rip the white from the black. Normally the black and the white were attached together back here, and you have to rip that black away from that white. Well, when you do it in a generator and so forth, a whole different story. You're doing pushing. You're pushing field against field. Here, we don't have to do anything. We just pushed it into a Venturi, and the Venturi did all the work. It kept the black away and squirted all the white out. It's very, very simple. And you could have literally thousands of these in a little handheld device. Hold on. Something similar to this. And you have thousands of these literally inside here. These are tiny, almost micro size. And they would just turn online as needed. And you could also have run into batteries, just cradle it into a battery, and the battery would be all charged up. But this could be a walk-around portable by itself without a battery. I don't know I don't think you need a battery, but it wouldn't hurt to have one. You're going to need some kind of a battery to fire it up, because you got to get the laser going. Once you get the laser going, you should be able to get more energy than you're putting in. So the laser itself is charging up your battery or running your devices and whatever through these devices. But a little tap off of there you use to keep the laser going. And you're supposed to get huge, incredible amounts of energy if you can create these electron showers, and there is zero question we created them. That's no question whatsoever we can create them. All right, listen to this now. What happened was I was rejected by everybody when I started to show my electron flood theory back, 2015, 2016, right in that area. So I ended up going to the University of Geneva online through Coursera, and I was able to interact with the professors and everything. I showed them all my stuff, and they were nice. They weren't nasty whatsoever. And they said, well, how did you take these pictures? And I said, I use CMOS. And they said, you can't take pictures like that because of they would damage the CMOS. And I said, no, we're using light. Light is made to be seen by CMOS. That's what it's all about. They were using big particles like this. We were using the little particles, and these sensors are made to be excited by these little bitty particles, not big jobs. What they're doing is they're hitting them with things like this, and it destroys the metals inside and ruins the CMOS. So they were right. You couldn't do it with their particles, but we could do it with light. We could see it with light, and we were accelerating light. We weren't smashing these to bits. We were smashing light into its two pieces. It only had two pieces. All right, so it all started here. Now, this is 10 years ago. I think it's time to look at this. And I know they are looking at it, but they won't look at the stuff I show because nobody can stand in front of it and say I'm wrong. But what really did happen was kind of crazy. Fermilab said, don't ever contact us again. You're a tinfoil hat guy. Exactly what I was told. And they've never backed down from that. And it was Don Lincoln. It was that article, this exact same article that I was referring to. I said, we found these particles. Will you take a look at this? No, you're a tinfoil hat guy. This is all this and nonsense, and you don't know what you're doing. And we went back and forth a number of times because I didn't accept it. And he's still wrong today. Today's just like another day of being wrong. This is his stuff. This is from Don Lincoln. This is our stuff. There's no difference whatsoever. And so anyway, here's what happened. I go to University of Geneva for particle physics, and again, I interacted. They were very nice. And I said, yeah, first of all, you have to focus. You guys aren't even focusing. They were just sending them around in circles and hoping something would hit head on. They're not going to hit head on. They have such a strong field that they just nuance away from each other. To hit head on is almost never going to happen. It would happen here and there, but very rare. And we could focus ours all day long. We're focusing. We're just sending it right through here all day long. We don't have to stop. Now, I don't know about how long you could do this for. Is it going to be erosive something's probably going to happen here. I don't know. Maybe you have to use ceramics. I don't know. there's a lot of engineering to do here. This is no little thing like that. But I think coming in here, you should be able to have an increase in energy. Luminosity is energy. There's very little luminosity here, and there's a ton of luminosity there. And I believe this is all you need right here is that white to fill your batteries up. And if you could put a receiver on there, I think I showed this before, but I can't show it enough, because if this worked, we're good to go. And we could get away from all this destroying the Earth stuff. I know everybody says, oh, they'll kill you for showing something like that. Well, so be it. What are you going to do? We got the whole Earth is being destroyed. I don't care what anybody says. You can just talk in these circles all you want, but we are destroying the water. We're destroying everything, and it's all based around energy. We need energy. And what is this? This is energy. As far as I'm concerned, that is energy, and I'm talking about on steroids. Because these particles, fields here, the only reason you see in that field glow like this is because it's gaining energy, because it's being sucked into here. The only reason you see these ones are glowing are because they're being radiated backwards. And look at the glow on these babies. They're here. You don't see them. You don't see them until this explodes backwards. That's what's called reverse EMF, reverse electromotive force. And you can see it back here. You see those fields? See the backwards facing fields? Those babies got some power. That is serious, serious stuff, my friends. So anyway, CERN, the next thing I hear is CERN is going to shut down to put in focusing magnets and CMOS. I'm not kidding you. They told me, they said, first of all, they started out by, no, you can't use CMOS. I think I might have told you this. And I said, yes, we can, you can't. You'd be using particles this size, we're using particles this size. We're not going to hurt it because we're using it for its design purpose. So they did something to harden it. So I thought this was really interesting. After I showed them all my stuff, they shut CERN down and they put in more powerful focusing magnets in this upgrade they did. They put in focusing magnets and the CMOS at the same time, new technologies for the high luminosity. That's what I'm showing you is high luminosity. If you don't see this as high luminosity, I don't know where your luminosity scale ends. This is high luminosity. So what are they doing? The same thing. Whoops. They're doing high luminosity LHC technologies. And what do they need to do this? They need focusing magnets, otherwise the fields are not going to give you that high luminosity. You can't get it. All right, and in addition to that, they needed to do this, put in the CMOS detectors. This is just exactly what we were doing, but we're using light. So they're doing, and you don't need to do it on this industrial scale, these huge particles. You could do it on the subatomic level. And then you're only working with light particles, so there's really no danger. There's no, I think you're going to get more efficiency working in that range than working in the big range. But anyway, they put in the same thing, the CMOS detectors and system developments for the LHC detector upgrades. And this was 2019, and they upgraded, and I think 2022 they came back online, and they're doing very well. See, here it is right here, look at this. This work focuses on the design and integration of novel radiation hard, because that's what I said, you got too much radiation. They're putting in radiation hard, monolithic CMOS pixel sensors for the new trackers. So all of this was integrated, focusing and CMOS, and then they can see it, and it's, I guess it's going pretty well. Okay, yeah, I believe they had a 3-year shutdown. It opened on the 22nd of April, 2022. The LHC, Large Hadron Collider at CERN, restarts. And I guess it's going pretty well from what I've heard. I don't have too many contacts there, but it seems to be working out pretty good. But still, they're hitting things head on and just getting huge debris. We're focusing in and sending our particles in as a literal beam of particles. Look at this. Why can't we put a harvester right there, as I showed over and over and over, and I keep showing it until somebody tries it. and put it right here so that it doesn't hit these. It goes right in down here, and then eventually it wants to get to those and spin, make something spin, wheels, tires, heaters, I don't care what you make it do. But once this wants so desperately to be attached to the black, or vice versa. Well, no, it's got to be the white is seeking the black more than the black is seeking the white, because the white will go through the wires and end up getting to where the black is. It doesn't add any weight. It just pushes everything else out of the way in front of it. Okay, look at this carefully. This is the Venturi facing towards us, and Rod took these pictures and right into the Venturi. So in this area here, all we have is white. We're not seeing any Higgs fields. The Higgs fields are coming back together on the periphery, and then they will start to come back together as we come back towards us. But here we can see something that I never saw before, and I have never seen since. And I have more pictures of light than anybody that's ever walked the face of the planet. I can absolutely guarantee you. Rod was prolific and magnificent. Now, all of these are just standard looking Higgs. This I thought was very interesting because it did change color. Color is a product of spin. And you can see it's being crushed. You see it being crushed here, like, and it's like stretched a little bit. That increased its energetic value. Now, that's just something that was caught my eye. But then I looked over here and I saw that. And I said, what is that? All right, can you see that? Let me come down a little closer. All right, sometimes it gets squirrely looking when you get too close, like that right there. All right, this is good enough. Why is that bright spot like there, and why is it sort of curling around towards this direction and in the middle of where it shouldn't be? I mean, everything else, and I've never seen that ever happen before now. So I went through tons and tons of video, anyway, I think I found a particle. But look, I want you to remember this, because I show it all the time. You see this little spritz of light coming up there, bang? These are the things that are creating these spinning disks. These little spritzes, they come out and they whack something and start spinning it. And they're all coming through here basically at the same energy level. That's why you have sort of a coherent light out here, which is red, because it came through in a red spin. And it's a wavelength, yes. It's a spinning length. You call it wave, that's fine. But it's the length of the frequency. All right, it's the easiest way to show it is that little wave. And that's the length of the spin. All right. I think I've shown that pretty well. Now, again, what it is the less energy, the longer the spin. All right, when I say energy, it's impact. Energy is impact. When that hits something, that's energy. As it's just going, there's really no real energy is slowing down because it's interacting with fields. But when it really whacks something, it hits it and then it bounces back this way. The color of how hard it hits something. If it hits a pillow, it goes boing, and it just sort of bounces real slow. If it hits something hard, it goes bang, and it pops back quick. That's why we see the different colors, as I explained before, I believe. So what is that? What the hell is that? All right, I got the lights off in here so that you can see a little better, but don't forget, this is the particle we're going to be looking for. And where did I have it? I have it here somewhere. That particle showed up right here, I believe. You see right here? That white particle, All right, I think that it was spinning backwards. So, in other words, these all spin on a right-hand spin, this direction. And they're supposed to do that. They all do that. All right, and the one on down here is doing correctly. But this one's going backwards. Now, what will that mean? It strips off the particle. The particle's being stripped off the edge. There it is right there. Imagine that. If that's right, I mean, I don't see any other way to look at this. This took me years to figure this out. I mean, and I think I got it figured out now. Let me turn the light on so I can point things out. All right, don't forget, these particles are coming down, spinning with what they call the right-hand rule. Spin, 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 spin. Well, this one here is going backwards, and it's gathering the energy into itself, I believe. And then when its field concussed with this field, its particle, which is on the outside of its field going this way, got scraped here and stripped off and is spinning now this way. That's all I could take from. That's the only part. That's the only picture I have of anything close to this. And I think this was from that event where this white particle was produced. And all this stuff was done with this phone. All right, like I said, this goes back to I think 2012, and the pictures are just stunning, absolutely stunning. Look at that. These are Higgs. I call this Higgs on the move. And that one there, remember I showed you another one where the field got crushed and it turned bluish looking? Well, this is the same thing, only this one really got crushed. Because they're coming through here the same wavelength, the same energy value, basically. And this one here got pinched and elongated, and it's now slowing back down again. But, you know, that's pretty interesting. All right, I suppose this gets boring after a while, but this is what everything has to change. Everything, I mean literally everything. Because we don't understand even what the tiniest particles are made out of. Gravity's not understood. You know, the scrub of space, where the vacuum of a space, not a vacuum, all of these particles are particles of light. Light is really a liquid in space. It's virtually a liquid in space. You don't see it, although it's flicking on and off all the time. And even Don Lincoln from Fermilab says it's the quantum foam. It's like fizzing on and off all the time, which it is. Particles of light hit other ones and they blink and that's it, they're gone. He says they call it like the foam on root beer, and yes, it's writhing foam, yes. All right, this is cool. This is, again, Don Lincoln, and again, we didn't hit it off too well. He thought I was just crazy, but he wouldn't take the time. He told me, I'm not going to look at anything you send me. Don't bother me. This is him talking about the quantum foam, exactly what I say. Empty space isn't empty, absolutely not. He says the foam on the head of a root beer is complicated. It's bubbles appearing and disappearing, dizzying display of change. Empty space experiences similar activity, subatomic particles winking in and out of existence. Why would that happen? These ephemeral subatomic particles are real and have a measurable impact on the universe. All right, so what does that mean, Don? What it means is there's particles of light banging into other particles of light. What does that mean? It means light slows down. What does that mean? The redshift doesn't work as far as judging where we are in the universe. All right, the universe is absolutely saturated with fields, and I can prove that too. So again, they realize these things the space is saturated with particles, but they never consider how much that's going to affect the movement of these particles we call light, which is supposed to never change speed. We know that's not right. I'm showing you can change speed as much as you want. And this is what is out in space as far as fields go. Now, this was Rod's nephew, Dylan Carpenter. He sent me these just out of the blue. He said, "What do you think?" I said, "Whoa." He got some kind of new cell phone. Or I'm telling you, these phones can pick up all of these invasions into the metals. Basically, that's what it is. These are complementary metal oxides, silicates. It's on a substrate with some things that can pick up different frequencies and then send them to some kind of a processor that says, okay, that's dark, that's light, that's blue, that's green, whatever. That's beyond me, but I can tell you one thing, it works. And these fields are out in space, they're everywhere, and everything's a dipole. You see it black and white everywhere, black and white, black and white. black and white. Everything is literally a dipole. I can't find anything. Well, there is nothing that's not a dipole. And here's what they're looking for. This is a doodle that came from CERN or somewhere. And they're showing the black particle out here and the white particle over here, dipole. They're calling them gravity waves. Well, they're just basically big dipoles. You see that? There's that's ours. Now, what do we got? Oh, this is no. See, look at this. That's a dipole. You don't get any more dipolar than that. And again, this is Dylan just sent these to me. I got a feeling this could be Venus, because Venus spins in reverse. It goes around the sun in the same way we do, but it spins backwards on its axis. Not fast, but it does. You see, it looks like it has two fields, one here and one here. And this would be the axis of rotation. And so it's spinning, it's going through the universe the correct way, but instead of it's rolling like a tire down a road, it's going backwards, scrubbing real hard. And that's why you're seeing such a serious dipole reaction here. I think. That's my take on it. But I could be wrong. And probably am. All I can tell you is spinning particles creates these type of fields like this. The moon does not. The moon is not creating a field because it has no axis of rotation. It's just plowing forward, creating blue hue in front of it where it's pushing against and crushing the light, yes, and stretching the light in the back more to the reddish spectrum. So yes, it does interact with the surrounding atmosphere, but not the way a spinning particle does. And it just appears there's something to do with the spin. It goes a boom, 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 as it goes around, creating these field effects. They all do it. They all do it. Okay, I guess I'll leave it at this. But this is about the quarks and leptons. Are they the smallest particles? And here's Don Lincoln again. And this just goes back a few months ago. I know, and I've been putting it out over and over. I've been kind of getting a little pushy about this too. And I can see that he must be responding to my, discussion, because I haven't been quiet about this. He's been holding up my research because I presented all this to him, and he refuses to engage. He calls me a tinfoil hat guy. So, and I don't hold any grudges. I just like to get this started and get looked at. That's all. If I'm wrong, I'm wrong. But I think I've shown enough to present a very, very solid case. As far as I'm concerned, that's what it's all about. My case, I think, is more solid than his. These are the big questions, the ultimate building blocks. The ultimate building blocks are these dipole electrons. Right there is a dipole electron. In that capacity right there, it becomes very reactive. It's normally considered heat. When they're in a blob like that, at 1823, they become stable. It's called resonance. There's got to be some hum that causes this thing to shake just right, and boom, it locks in. If you look up salt table experiments, you'll see at a certain frequency, it gets a certain pattern. A little higher, and it gets a really nice, absolutely gorgeous patterns. So all I can say is I wish Don Lincoln would discuss this with me and look at some of my experiments, and maybe he can duplicate it. I mean, that Fermilab's a pretty big place. Now, I know I'm intrusive, and I know this could be a problem for them, it's always better if you don't solve something if you want funding. if you solve it, it's over. So I don't know what else to say, but I think we deserve to have this looked at. This is not nothing. This is not nothing. This is something. We started with light. We ended with light. CERN shut down and went into focusing in CMOS. You know, I like I say, I went to the University of Geneva. I told them all this stuff. They didn't fight with me about it. They just said, we'll follow you on Facebook. I got thrown off of Facebook, so I lost everybody. I lost all my contacts. I lost everything. And I don't know why I got thrown off of Facebook, but I did. And I'm back on there now, and now I don't do much on there at all anymore. It's all on my YouTube channel. But if we don't pay attention to this, which is starting with the particles of light, and they are now. As a matter of fact, it's all over the place now. Mini accelerators. Hold on one second. All right, this is really outrageous. This, I believe, goes back to 2014, 2015, right about in that area. Some Russian experiment. And they were in outer space in the capsule, and they had a vacuum chamber, which means there's nothing in it whatsoever, no gases, no particles in it, it's a vacuum. And they injected charged particles into it, which means particles that had extra electrons, basically, which are these white particles. Then what they did was they shot light in here like a camera shot, basically. And here's what they saw, and they freaked out. Everybody went crazy. How could this be? And they still haven't figured it out. I think I got it figured out what they're looking at. As you know, we could separate the black from the white, and there's apparently charged particles are these extra whites. They're all in here, pushing the black to the center. And they will. The black doesn't mind being right on top of each other. The white, forget about it. But they pushed all the black to the center. Now, they shine in a light here. Now, think about this carefully. All right, take your time and think about it. So you say they can't. The Earth guys couldn't believe what they're seeing. Nobody could. What does dark matter do? It doesn't absorb. It doesn't emit. It doesn't reflect. It's just dark. It's exactly what we're seeing here. We're shining light on it. It's not bouncing back at us. Why can't we? And it doesn't absorb it. So I don't know what's going on. Whether it's just rotating around, because you can see it actually. It gets. I think they're shining the light more this way. And this is more or less an egg-looking thing. You see how it's cloudy looking in the back? This is some of this is guess, but these particles are the charged particles. These are the electron parts. These are the glowy parts. And the more you push against them, the more they glow back. That's why these are glowing, because we're shining light into those particles. And they say the more you look at them, the more they glow. Well, that's true. This is not going to do anything. It's just dead. It's dead in the water. You can't see behind it because it's a ball of darkness. And we found the same thing on the other experiments. Once this gets on top of the white matter, you can't see the white matter anymore. And that's the only reason you can see the black. In this case, they're shining light into this, and it won't reflect and it won't emit. So it's just black. That's my take on it. And it looks to me like it's actually flaring off the edges and then coming back in, which is something that light would do. I mean, these are little reactive magnetic particles. So there's a lot to look at there, but you can see the black just separated off. There appears to be a ton of black just laying around waiting to attach to the white. All right, I'm going to finish it up with this. What we need to do is create electron showers. Why? Because the energy of neutrinos interacting creates it to 100 giga-electron volts to a few trillion electron volts. You have to create the electrons and muons, which is exactly what we've been doing. So this is the physics of electron showers. And here's what it looks like in their visual statistics. These are the electrons. They come through low energy. This is very low energy. Low energy. See low energy? The shower creates the high energy. So we're going from low energy to high energy. That's understood. What happens to the muons? The muons back out. And that's exactly what I have shown. Precisely. All right, here it is right there. They go extremely high energy to the white, and the muons just back out. And we get these extremely high energy showers over here. And it's just explosive. I mean, just absolutely. That's a subatomic nuclear explosion. That's exactly what it is. Subatomic nuclear explosion. On a desktop, and I don't think it can hurt you. I don't see how that could hurt you. You know, it's going to be back together spontaneously, instantaneously, without delay. And again, the electron showers, if you can, what they're doing is proton-proton collisions. So they have to make this big smash of stuff. And then they get a large number of these hadrons. And then they have to decay. And then they decay into the neutrinos. And then the neutrinos create these gigavolts up to teravolts. But they had to start with protons. We're starting with the neutrinos right away. These are the energy of the neutrinos. That's what we want to get to. We already started with neutrinos. These are neutrinos that are splitting off. All right, here it is, right here. Electron neutrino, muon neutrino. Those are neutrinos, the black and the white. They turn into the shower. That's where you want them. That's your energy. I see no reason we can't do this. I see no reason whatsoever, but I can't do it myself. You just saw electron neutrino, muon neutrino. Here they are. And again, my little doodle here says if we can get that white stuff squirted on here and coming down, we're in good shape. The other good guys, what they're doing is they're smashing things and then digging through the debris and then doing it again in another hour or something. Well, we don't have to do that. All right, they're doing this. They're making these proton collisions, bam. And then they got, what are they going to do? They got to somehow harvest that stuff up, and we're just continuously spraying these high energy electron neutrinos. Only the white ones. The black ones you don't want. The black ones you do not want. They are not going to help you. It's what the ones that you want are these ones right here. All right, the black and the red just shows exactly what Fermilab said, and you want to get that black away from that white. That is not easy to do. And the only reason it is easy for us to do is because of the Venturi. The Venturi, a little tiny slit there, and it's angled in like a scoop, and it forces it to restrict. It's like basically like a garden hose. And when it does, the black ball being the same exact size, you see it here? The same ball is over here, same ball everywhere. See the exact same ball, exact same ball. And the only reason we can see it is it's on top of the white. It's on top of the white. And they immediately grab back together to that white as it just barely gets past the Venturi. And then they recombine into a photon. All right, so the case has been established extremely well. And we can show that the black can actually push the white in front of it. As if you tune this Venturi correctly, there's a lot of things can be done. I can't do this anymore, and Rod, I don't think, is interested in doing it anymore, so somebody's going to have to take over. This is the Whistler waves, they call them, and that's ahead of the pulsation. All right, this is strictly the white particles pushing bump, 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 and they do it really quick. The black is just a wave. And that's why when the atomic bomb goes off, you can hear a Whistler wave here. And then 30 seconds later, boom, the black particle comes and hits. But you can hear this way off here instantaneously. There's a lot to learn from dipole electron flood theory, my friends. And I mean, we could even maybe get some help in the energy sector. Who knows? But they know that there's new physics are required now. Everybody knows this. They just sort of skirting around the edges.